is next, and he's going to talk to you about the voids, which is a really, it's quite personal to me because I have a huge void in which I call my stomach, and always needs to be filled. Also, one of my friends wrote about me needing to find someone to fill the void, literally and figuratively, on a Tinder bio for me, without asking me. But I mean, I left it on there because it's a good talking point. So everyone give Nick a round of applause to come and talk about the voids.
All right, so hello, I'm a theoretical physicist, so I apologise for that. This is a pretty picture, isn't it? No, not that stuff, all this black stuff, because that's what I work on. And I'm going to try and convince you that empty space is not boring and uninteresting, but actually pretty amazing stuff. So let's make a quick analogy. If you go back 1,000 years or so, well, it's a bit unclear, but I suspect that people didn't really understand that we lived in an atmosphere. They thought that all this stuff around us was just empty space. And then they had ideas of, there were these sort of demon things that blew past you. There was wind and all of that sort of stuff, and gases that you could see or something, but they would have thought that all of this was just empty space. And of course it isn't, and you've now been brought up with the idea that you live in an atmosphere and there's gas, and so you never think twice about it. Well, I want to try and convince, I guess actually before I do that I should say, when this was all resolved from the science point of view was actually right back at the start of science. So Galileo's student Torricelli actually managed to show that it was possible to make a bit of space which was different from this, because it doesn't have atmosphere in. And it's rather cool, because all he did was that he took a tube full of mercury, and he just upended it in a bowl of mercury, and then all the air pressure of others is pushing down, and it pushes up a column which weighs the same, a column of mercury that weighs the same as the atmosphere that's pushing down. But if you make the column too long, then you're just left with a hole. And that's where vacuum is. And so people spent a lot of time discovering about what air was and what vacuum was as a result of that. But I don't want to do that today because I don't have long enough. What I want to do instead is to try and convince you that there's another thing that's even more amazing about empty space that's come about in the last 50 years or so based on theories of the last 80 years or so. When we understand the quantum vacuum, we come to understand that the properties of everything that lives in empty space is basically determined by that space. Alright, so to convince you of that, I've got to take you into the weird and wonderful realms of relativity and quantum mechanics, so I'll try and be as gentle as I can. Let's begin with our friend Albert here. So he declared something about our universe which is really completely stupid, which is that the speed of light is the same for any observer. He basically said that there was a maximum speed in the universe and nothing can travel faster than that. It just happens that light travels at that speed. So look, what are the consequences of that? So imagine some lights travelling along at the speed of light. I'm pretty fit, so I'm going to run along with it. And if I could run at the speed of light, then I'd be travelling with it and it would look stationary to me. Albert said that wasn't possible. You have to see the speed of light as being the same whoever you are. So it means that nothing should be able to travel at the speed of light. That's this idea of there being this maximum speed limit. But then he had to go and take everything that, when you were back at school and studying physics, they told you things like, if you kick a ball, it moves faster. If you kick it again, it goes faster again. And he had to actually say, well, at some point that has to stop. As you kick it, it may go faster for a while, but eventually when it gets very close to the maximum speed things can move at in the universe, then things have to change. So he had to go and change the rules. And what he did was when you kick something, you give it some energy. So he wanted an expression for the energy, and look, you know where we're going, right? E equals mc squared, we all know that. But that wasn't what he was trying to do at all. What he wanted was this horrible square root thing here, which people don't normally show you because of they're worried about your sanity. This says the velocity, v is the velocity, it's the speed that something's moving at, and c is the speed of light. And what this factor does is it says that if the speed were to equal the speed of light, this fraction here would be 1, and we've got 1 minus 1, which is 0, and then we've got 1 over 0, which is infinity, and there's a square root, but don't worry about that, it's still infinity. This is an expression that says that if you make something travel at the speed of light, you need an infinite amount of energy, and I don't think any of us have an infinite amount of energy, so you can't make something go that fast. So that's what he was trying to do, and then he went, oh yeah, and I better just check that when v is 0 and the thing's stationary, that it doesn't have any energy, so then this is just 1 and you scrap this. Oh, you get E equals mc squared. And bizarrely, actually, it does drop out like that. It wasn't in any sense trying to derive it. Anyway, so this is the first thing that we need to take away, the first sort of bit of new physics, which is that actually the mass of a particle, the sort of the thing that gives it its bulk, is a reflection of energy that is stored in that particle. And particle physicists use that all the time now, so we take some energy and we scrunch it down into a little bit of space, and we let the universe say, oh, right, we'll make some particles. We can make the mass of particles using it. Right, cope with that? Let's do the other weirdo, wonderful theory of physics, which is quantum physics. So we talk about particles, but actually none of them really are particles. Fundamentally, everything is associated with fields. So this is like the idea of electric and magnetic fields. You know, when you take two magnets and you try to push them together, there's sort of something between them that causes the force between those magnets. Those are fields, things that fill space. You can think of them like waves, like water waves. So where do particles come from then? Well, this is because of the strange behaviour of quantum physics, which is, for some reason, like if you take a water wave, then the energy is distributed out all through. And you think, okay, well look, if I want to take the energy away, I can just turn on a tap, and the water will just, the energy will just sort of gently pour out of the water, and the wave will go flat. Well, actually, it turns out, just in our universe, the way that it is, that as you get down to the last bits of energy, it doesn't just continuously flow out of the wave, it comes in little drops, which we call quanta. And so this is where particles come from, because if I come up to this wave and I tap it here, you might think it would just give me a little bit of energy. But right at the last minute, it has no choice. It either gives me a big lump of energy that comes from all over the wave, or it gives me nothing. Well, if it gives me nothing, I don't notice. But if it gives me a big lump of energy, I think, wow, I just hit something. And that's the idea of a particle. Right, and so, you know, the photon is the particle associated with electric and magnetic fields or light waves and so on. Okay, so of course, this is rather peculiar, and this is the classic experiment that makes you think about just how weird it is. So you take, say, a light source, but it could be a source of electrons or any particle you like, and you shine it on two holes in a bit of paper. That just creates two copies of the light source. And then you look on the other side, and it's like you've got two wave sources. You chuck two stones into water, produces ripples, and then the ripples mess about with each other. We call it interfering. You get points where the peaks of the waves come together, and then you get a big wave. And when the peak comes along, and there's a trough on the other one, and they cancel out. And so you get light and dark patches if you put a screen on the other side. And this is all perfectly sensible and reasonable if you think that light is a wave. But when you get down to those last lumps of energy, this is sort of typically the amount of energy that a single electron in an atom has. So it's very small bits of energy. But the last bits of energy sort of come through like bullets. And then you think, well, where on earth does this crazy pattern come from if there are bullets coming through here? And the answer is that actually they do. If you sort of put lots of bullets through, they eventually sort of accumulate in this pattern. So they do know about it. So if you want to describe this thing in terms of bullets, maybe you shouldn't, maybe you should think about it as waves. But if you do, then you have to change the rules again that your physics teachers taught you. And the best way to understand it is with something called the Heisenberg uncertainty principle. So if you think about this as being a cricket ball that you're chucking through here, then the way in which things get changed is that over very short periods of time, you get to cheat about the amount of energy you've got. So normally energy is a constant, it doesn't change, there's a certain amount, you can heat one thing up but something else cools down on that. But here, just for a little while, you can just cheat. The universe can just cheat. You can say, look, you know, typically the sort of time it takes for light or something like that to go across an atom, you can just make some free energy and do what you want with it. So what that means is that if you sit here and say, right, I'm having none of this wave stuff, this is a cricket ball, it's going to come through here, I'm going to tag it, there it is. The act of pinning it down to a very short period of time lets it go, I'm going to borrow some energy, and it can even borrow enough energy it can nip off and go through the other hole without you noticing. And so that's sort of the way in which quantum theory puts together this idea of particles and fields. But the only thing I want you to remember, I want you to remember E equals mc squared, and the other thing I want you to remember is that for short periods of time, the universe gets to cheat and just grab some energy from nowhere. It does have to give it back again eventually. All right, so those are the two things that I want to put together to blow your mind. Right, so I want to think about what these two things mean for empty space. So the first of all, it's true of the vacuum as well, of just a bit of empty space, that over very short time periods, it can borrow some energy. You say, oh, I'll have some energy, please. I'll give it back to you in a brief period of time, but let's have that energy. But then relativity tells us that we can use that energy to make particles. And that's what happens. Empty space is actually this froth of stuff that keeps appearing and disappearing. So the electrons or quarks or whatever you want to think about appear for a little short period of time and then they disappear again. And so it's typically the time it takes for light to go across an atom. You don't believe a word of it, right? How on earth would you know that this was going on? Well, the answer is that you can see these things. If you take two electrons, bingo! Sorry, people like you, what causes unrest? Right, so electrons repel each other, and they do it, as we've said, by electric fields between them. But you can think of it as the lumps of energy in those fields, which are called photons. Okay, so you can think of an electron as interacting with another electron. They sort of send a photon between them, and that's how energy and momentum gets exchanged between them. Look, this is basically just Coulomb's law that you might remember from when you were at school. You can do the calculation and you can work out how one electron scatters off another electron. And it's great, it works. Until you start to do your measurements down to about the 1% level. And then things start to go awry. You don't get the right answer. Because you've forgotten that ridiculously, from time to time, the universe out of nothing will suddenly create an electron in the middle with this free vacuum energy. And well, of course, that's a charged particle, so it interferes with this photon, which is going from top to bottom between these guys, and it just changes the process a little bit. But that's okay, because you can calculate this if you believe these things exist, and then you can check that it gives the right answer. And this theory, called quantum electrodynamics, is the best physics theory we have. You can do calculations down to 11th, 12th decimal places on some processes and get the right answer. It's miraculous. These things really exist. So empty space is this froth of material. Oh, yeah, so look, we get bored of drawing these diagrams, so we like to think like this, but there's a way of encoding that, which is basically the further apart the electrons are, the more likely there is that there's froth between them. So you can encode this physics as thinking about the electric charge of the particle, we call it the coupling, but it's the electric charge of the particle, as not being constant, but actually something that changes depending on how far away you are from an electron. So here we go, this is the electric charge against the separation of the two electrons, and it changes. Actually, it changes by a very, very tiny amount. It's a few percent effect over all of the energy scales or distance scales that we've ever probed electrons. But this is just to convince you that it's true that this froth is really out there. Alright, now we're going to do a little bit of nuclear physics. I'm going to find something even more miraculous. Right, so let's remember atoms. Atoms look like little solar systems, kind of. There's a nucleus in the middle, about a 10,000th the size of an atom. In there are positively charged protons. Depending on how many of those you have an equal number of negatively charged electrons. Depending on the number of electrons you have, you get a different atom. So you get carbon or hydrogen or so on. But let's think about those protons stuck down there in the middle. So why on earth are they stuck down there? Well, because there's another force. Right? They're positively charged. They want to fly apart, actually. But there's another force called the strong nuclear force that sticks them together. Actually, even that's not quite true, because it turned out in the 1960s, some stupid names coming soon, that people smashed up protons and they found that they were made of things called quarks or quarks. These things so strong. These things interact very strongly, at least 10,000 times more strong. That's why the electric forces between the protons and the electrons. That's why the nucleus is so small. We have a good theory of this. The interactions between the quarks. Oh, that's the thing I was going to say. So actually, the interactions between the quarks is even stronger than that. What's left over here, which ties the protons together, is just kind of the leftover forces of when these quarks have been bound together. So this is really an astonishingly powerful force. Like it's just hidden in the nucleus. Okay, so we have a theory of this force, and it is like our theory of electricity and magnetism. There are charges. There are things like photons that they exchange in order to cause attraction and repulsion. However, in this theory, nature's gone a little bit more interesting than it did with electricity and magnetism, because there are 3 different types of charge. That's actually why there are 3 quarks in a proton. They're both all 3 of them are things that can be positive or negative, like normal charge can be. But there's just 3 of them, and that makes the theory a little bit more exciting. And in particular, when you go and you look at the vacuum froth, and you look at the effect it has on the interactions, not between electrons now, but between quarks, something really bizarre happens. If you take 2 electrons and you put them on top of each other, they interact a lot. If you take this one and you send it off to the Andromeda galaxy, this guy doesn't care anymore. But quarks are exactly the opposite. If you have 2 quarks on top of each other, they don't interact at all. As you separate them, they start to interact more and more, which is very peculiar, but it turns out to be what comes out when you calculate it in this sort of force. And it has some remarkable consequences. The first one is called quark confinement. So if you reach into a proton and grab a quark and say, right, I'm going to take this away and I'm going to show everybody a quark, as you pull it away, the force that brings it back into the proton, the restoring force, gets bigger and bigger. Eventually you run out of puff, you have to let go and it goes back in. So quarks are confined. You can't ever extract one from one of these particles like the proton or neutron. There's a whole bunch of them called hadrons. Okay, so some people don't like that, but as I say, it's a perfectly plausible way for things to be, and you can calculate this theory and it makes sense. But let's think about what it means for the vacuum. Right, so we said the vacuum, empty space, it creates some energy out of nowhere, cheats. It uses that to make some particles. We said electrons. Now let's say quarks. Produces 2 quarks on top of each other. They don't interact. They start to separate, because, I don't know, they might have some energy, so off they go. And they start to interact more and more strongly. They're attracting each other. They want to come back together. So look, think about a candle. In a candle, what happens is that the atoms get excited. The electrons move away from their atoms. They want to come in. They're attracted in to the atom's centre. They cascade down their orbits. They get closer to the nucleus, and they give out energy. They give out light. So attraction is all about things coming together and giving out energy. So what happens with these quarks is as they move apart, they start interacting really very strongly because this force is enormously strong. There's a huge attraction energy, that they want to give out. It turns out that that energy from the attraction is greater than the energy that the universe originally borrowed for a short period of time to make the quarks. So the universe goes, oh great, I make these things for a short time, I get some energy, I pay back my energy debt, I get to keep my quarks. And this is what the theory does. It fills up the whole of space with more and more and more quarks. And it packs them together until they're so dense that actually the force is starting to switch off again because they are so close to each other. So how dense is this stuff? It's as dense as the nucleus of an atom. 10 to the 15 grams per centimetre cube, and it's all around you, everywhere in the whole of the universe. Really? Wouldn't we notice, you think? Well, we do. This is where the mass, the energy that makes the weight of your body, comes from. The quarks in the protons in your body are constantly trying to move around. They're really basically massless. They want to travel at the speed of light and just go whoosh. But they can't because they keep hitting all of this enormously dense material that is all around you. It's the interaction energy between the quarks in your body and those quarks in empty space that make you able to sit in this room as a massive thing. How am I doing for time? Is anyone paying attention? I've got lots. I'm going for another hour. Fantastic. All right, so like I say, this for me was a fantastic discovery. It's as bizarre as discovering that we live in air, that we live everywhere in the universe in this amazingly dense material which describes and provides the properties of all the things that live in it. There's another part of this, which is the Higgs boson. So let me tell you about that. So it turns out that that's where most of the mass in your body comes from. Protons and neutrons get their mass from this quark goop that's all around you. But you can't in this way explain where, for example, electrons get their mass from, because they don't interact by the strong force. They don't know anything about this background stuff. So that was a puzzle. And then we started to find other particles in particle colliders which just have ridiculously large masses. There's a thing called the top quark, which has a mass 175 times that of a proton. And you can't get a number like this out of a theory for free. The density of the quarks in the background basically explains the proton mass. If you want to get something 175 times bigger, well, if you're Peter Higgs, up in Edinburgh back in the 60s, you propose that you've got to repeat the trick that you've just seen, which is that the vacuum must be full of another sort of material, which is about 100 to 200 times denser than nuclear matter. And now, he didn't call it the Higgs, but we call it the Higgs after him. So this is some new material that fills the vacuum. It interacts by a new force with all of the particles in nature to give them, for example, the electron its mass, or these guys their mass. So that's what he predicted. Actually, so it's quite funny because he predicted it and everyone went, yeah, but how would we know if the only effect is that it gives mass to things? I mean, it's fairies, isn't it? And so that's basically what the guy who reviewed his paper said, and he had to go and scratch his head and suggest a way in which you might be able to see a testable version of this. And what you basically try and do is that you try to cram so much energy into a small bit of space that you can disturb this stuff that makes up the background. If you do that, you can actually put the minimum lump of energy that will do that. That's what we call a Higgs particle. And that's what we've been trying to create for probably 40 years or so at our particle colliders. So my experimental colleagues have a toy. It's called the Large Hadron Collider. It's about 28 kilometres round, about 100 metres underground under Geneva, in which they collide things together. But the basic idea is you just take electrons or protons. In fact, they use protons at the moment. And you just try and collide them together. You kick them a lot, so they've got a lot of energy. And then you collide them together. You're just trying to cram all that energy into a tiny bit of space so that nature can use it to make new things, or in this case, to disturb empty space. So yeah, what happens when you collide protons is that you just get a mess of quarks. And that's no good because you can never detect anything from that. But very occasionally you get some interesting things where you put quarks in, and in this case you get laser beams coming out. Okay, you only get a single lump of light. But this is where you've created a Higgs particle, and it's decayed to 2 photons of light, which you can then detect. They look very different from the quarks that you've sent in to the original collision. Or it can decay into 4 electrons. Okay, and over here is the discovery period of 2011, 2012. This is just the number of events where you see 4 electrons come out, and this is where you add up the energy that they all have to see what it adds up to. And of course, you know, that energy is coming from this Higgs particle. This energy should add up to make the mass. So here we go. So the red stuff is what you expected to see. The black things are what you actually saw over time. And this was where things were happening, that there was an excess of events. You just saw, 15 or 20 more events than you should have done at this energy of about 120 times, 125 times actually, the mass of a proton. And this was the discovery of the Higgs boson, for which Peter got his gold. So this is all true as well. This stuff all around you is full of material 100 times denser than nuclear matter. I said I wanted to explain that it affects the properties of all the matter around you. So I've talked about mass. There's another thing, which is there's a force that causes radioactive beta decay. It's called the weak nuclear force. What happens there is, so it's a new force that happens in the nucleus, which rather mysteriously manages to turn a down quark, as it's called, into an up quark, which has the effect of changing a neutron into a proton. So that's one of the things that lives in the nucleus into the charged guy. And when it does it, it emits sort of the equivalent of a photon, but for this new force, which we call W's. And that W can then conserve charge. You have to produce something that's negatively charged, and so it produces an electron. This is what happens in radioactive materials, or many of them. That this process happens in the nucleus, and this electron comes whizzing out and bashes into your DNA and smashes it up, and you get radiation signals. Okay, so it turns out that all of this stuff that makes up the vacuum is charged under this force. So it's neutral to electricity and magnetism, which is why photons just whiz through it without seeing it. They don't couple to it in any way. But these guys just can't move because there's all this dratted stuff in the way. It's like trying to drive down the M3, So this means that these guys have a very, very large mass. And that's actually why this force is weak. And it's good that it is, because it means that the sun takes billions of years to burn, because it's this process that is fusion that's happening in the sun. So we're going to hang around long enough for monkeys to evolve into people like us. And it means that everything that's heavier than iron doesn't just decay away instantaneously. So again, the very structure of the world we live in is determined by empty space. All right, I should come to a stop fairly soon, I suspect. Right, you're probably still going, I can't believe all this stuff is there. Surely there must be some consequences. It's got to be mad. Well, one thing you might think about, and that people do think about, is the gravitational effect of all that stuff. So first of all, there's as much of the universe that way as there is that way, so I get pulled equally in both directions. So even though those forces are enormously strong because of all this matter around me, the net gravitational pull is nothing. However, in Einstein's general theory of relativity, what happens is that the effect of this stuff is just to make the universe very, very small. It sort of pulls everything together so the distances between things are tiny. And if you do that calculation with all this stuff that I claim that we're absolutely sure is there, you conclude that the universe could not possibly be bigger than about a grapefruit. It is, and that is the quantum gravity problem, or one aspect of it. This is a big hole in astronomy, in particle physics, in the whole of physics at the moment, that we don't understand how our quantum theories that describe the properties of matter with these strange vacuums interact in any way with gravity. We just get complete garbage. And this prediction of the size of the universe is often championed as being the single biggest theoretical error ever made, because it's like 40 orders of magnitude wrong from what we actually do. I'm not going to solve that for you tonight. I'll let you think about that overnight. You can let me know your answers in the morning. That is just an open question at the moment. I mean, one of the reasons is that you can't, I've talked about how strong the strong force is. Relative to gravity, it's just unbelievably strong. Gravity is just mind-bogglingly weak. And you just have to look at the fact that I'm wandering around here. The electric forces in a human being are sufficient to repel the entire gravitational attraction of the Earth. It's a big thing, right? Gravity is so weak that in our particle physics experiments we don't actually ever see the effects of gravity. And in fact, nobody has ever put two things closer together than about 0.1 of a millimetre and measured the gravitational force. Because if you put things that close together, then the electric charges on the things start to interact. It becomes really difficult to measure. So, here we're talking about looking at physics down to 10 to the minus 16 metres or something, and yet we don't even know what's going on with gravity below sort of the millimetre scale. So there's lots of stuff still to be done. Very good. Overview. E equals mc squared. You can borrow energy for very short periods of time, make stuff with it. The strong force then lets you pay back the bill and fill the whole of space with material. The Higgs is an idea along the same lines, and that's where the mass of your body comes from. Right, I'm going to stop there. Other than just to quickly say that this week I got into self-publishing. If you want to be even more confused, there's a 45-page write-up of this, which from next weekend will be on Amazon, and you can buy it for the cheapest price I could manage. Right, okay, very good, thank you.
And she was after your prizes. Would you be able to do us a favour and when people ask questions, would you be able to repeat the question so everyone can hear it?
I will do my best.
Before you answer. Thank you. And so now we're open for questions.
Okay. With this quantum vacuum, is it just a type of ether? Because I'm thinking in terms that when Einstein in 1905, he wasn't dealing with quantum mechanics. So when he was talking about special relativity, it would have been a classical vacuum. And so when you talk about adding quantum mechanics and coming up with a quantum vacuum,
I think the answer is yeah, it is.
It is a type of ether.
It's basically a sort of ether.
So it's a type of ether
that fills space. His ether didn't turn out to be true just because that's the way nature was, and this stuff turns out to be true. There's no intrinsic problem with the idea.
But it's all right, it's an ether, type of ether that obeys the Michelson-Morley's experiment.
Yeah, no, exactly. So
yeah.
it looks the same no matter how fast you move.
And so people should be really saying that the ether exists, but there's still a lot of people saying it doesn't.
Well, so the ether, as people originally imagined it, was a substance like water for light waves.
Yeah.
That's not true.
Yeah.
So in that sense, the ether doesn't exist. But yeah, the space is full of this stuff.
Okay, thank you.
First of all, thanks very much for the talk. Just to clear up of some of the things about quantum physics, which I've always found really hard. A couple of things I would just to clear up my understanding. You said so maths is kind of coming from this idea that there's a big vacuum, there's not a vacuum, that's full of stuff.
Yeah, I mean, so
And then which
everything
time I
around you
move through, is that like me moving through a fluid, like a football moving through a fluid,
Yeah,
and it
exactly.
slows down?
Think about honey, chuck a
Yeah.
ball at it, and the thing slows it down. It's
Okay,
very,
so
very similar. in
but
spirit.
when you throw something in space, it just keeps going. It doesn't slow down. Can you hear how?
Okay, so what's the answer to that? The answer to
Yeah.
that is that there are equations which describe how this stuff interacts with other stuff, like the thing you've thrown through it.
Yeah.
And those equations work in such a way that the only effect is that the thing moves more slowly because it has a mass. Okay, so you're thinking shouldn't there be friction or something
Yeah,
like
that's
that?
what. Yeah, that's what I want.
Okay, but the reason there isn't is that in order to disturb, what you do when you push a ball through honey is you make waves in the honey.
Okay.
And you dissipate energy.
Right.
But to give energy to this background, it's so rigid,
Yeah.
you have to give it the minimum lump of energy,
Yeah.
which is 125 times the mass of a proton. And most of the time, an electron, say, just in normal day-to-day life,
Yeah.
just doesn't have that much energy. It just can't disturb the background.
Okay. So if I kick the football hard enough, I'd eventually struggle, and that's where I can't get
Right,
past
you
the
rip
speed
this
of
stuff
light.
apart, the football would
Yeah.
stop existing and you'd
But
see
they
lots of
say
these
like,
particles.
I can't kick that football hard enough, so we never see it. So when we observe a space station go around the Earth, it never slows down.
Right, it just doesn't have enough energy to really excite
Okay.
this really rigid stuff.
Okay. The second thing I had was this strong force. So you had quarks in a proton, and you said that when they get pulled apart, they want to get back together again, which is great. But why? Why? What's pulling them back together? There's like
Well, so there are these three quarks, and they have, actually one of them has each of these different sorts of charges. And the
Yeah.
way it works, I mean, it's like, why does an electron want to be in an atom? It's because
Yeah.
it's attracted to the proton. This
Yeah.
combination of the three quarks is neutral. And they're pulled together to form these neutral things. So it's like the formation of an
yeah.
atom.
I just want to get my head around it, like a piece of string or something. That doesn't seem to work. Doesn't seem to be any kind of logical kind of. How can something get very far away and yet still want to come back?
It is odd, isn't it?
It's just like yeah. and then see the
Well, so I mean, there is this description of it where you represent it as a rubber band between the two things.
yeah.
And
Well,
then you
that's a
start to
nice
study.
description.
So then you start to study things called strings, and you look at string theory.
Okay.
It is very odd. I don't really know what to say other than that. You can believe either when you start breathing the electrons apart, there's this stuff in the middle that sort of shields them from each other.
Yeah.
It just, it comes down to a minus sign in the calculation. It's the other way round. That stuff in the middle sort of increases the apparent charge of those things. So they want to come together more strongly.
Yeah. Yeah,
So
I had a chat with one of my friends did physics as an undergraduate, and he sat in the car and he was like, "Oh, Alex, they're just making stuff up about colour and things like this." And like, honestly, I can't get my head around it. We had a good old chat about it, and I was like, "Yeah, that doesn't seem to make sense, but maybe us as humans
So
just
the
can't
thing
get
that
our heads around
no,
it."
it isn't. This is science, and it's just exactly. You don't walk out in front of a car because you watched a car and you know that that's a stupid thing to do. Science is just like that. It is just people who have incrementally observed things and gone, "Oh, it's like that."
Yeah.
Right. So I'm telling you about 100 years of loads of people doing that.
Yeah.
So I speak too quick. But this is just observing the way nature behaves, and it's true. It's true. I promise you.
I've been reading about antimatter, and people seem to be getting quite excited about the discovery of that. How does that play a part in what you're sort of mentioning, and why are people getting so excited about it?
Okay, so I can go on for ages about this. So what is antimatter? First of all, it comes about in relativity. And in relativity, you treat time like space. So if you think an electron can go that way, and it can go that way, you would think that there were electrons that could go forwards in time and electrons that could go backwards in time. And you go, well, that's stupid, right? But it turns out that the only way you can talk to an electron is through its charge. And an electron which is going backwards in time is actually the equivalent of a positively charged object going forwards in time. because we only see things going forwards. So actually, relativity predicts antimatter. It says for every particle, there are these solutions that go backwards in time. But when you recast them, they're antiparticles, things with the opposite charges going forwards in time. So it does exist. And I kind of didn't mention it because I didn't want to go through all of that. But you know, when I said that you can make electrons, that wouldn't conserve charge. So what you actually do is you pair produce an electron and a positron, its antimatter particle. They're created together, and eventually they come together and annihilate, and that's how you give the energy back. So they're a big part of that. And finally, why is it a big thing at the moment? It's a big thing at the moment because, look, if these things come together, an electron, well, so basically when an electron and a positron collide, what you're really doing is you're just scattering the electron backwards in time, in that way of thinking about it. So from that point of view, when you bring them together, they just stop existing, their energy remains. So that's sort of what's happening here. An electron and a positron come together and they give off a photon. And yet we look around us, and there's lots of matter here. There's no antimatter. If there was, we would be exploding into light. But in all of our theories, you always create a particle and an antiparticle together. So there's a big question of where's all the antimatter? And there's two possibilities. One is that it's hiding somewhere. So people come up with the idea that in the Big Bang there were two universes. One antimatter went that way and one matter went that way. But that's all a little bit speculative. What seems more likely is that fundamentally matter and antimatter in some ways interact differently. There must be new forces to somewhere out there that explains all of that. And if we could only understand all of that, which so far we don't, we would understand why the universe is matter dominated. Yeah, well, should I shut up? Ask me later.
Thank you so much for having me. Yeah, you